This is part 2 of the final video of this series, where we take an in-depth look at how service providers handle spanning tree on Layer 2 services. So in the previous video, in part 1, we took a detailed look at different topologies, different access network setups, Layer 2, Layer 3s, running spanning tree in the service provider, running ring protection, etc. And what considerations there might be for running spanning tree with the customer, propagating the customer's spanning tree, BPDUs, etc. And we also looked at how NIDs play a factor into handling spanning tree and how they uh, propagate or don't propagate BPDUs. We also took a look at if you use a switch as a NID, the problem with that, and uh, the constraints of how it can't forward BPDUs. It can either run spanning tree and peer basically with the BPDUs or drop them. So in this final section, we're going to look at layer 2 protocol propagation. We've talked a little bit about this already with propagating spanning tree BPDUs, but we'll take a more in-depth look at protocol propagation in general. And then we'll look at storm control. And then finally, we'll take a look at site redundancy and loop prevention with multi-homing. So this is kind of a big topic. It's very complex to do multi-homing with layer 2 services. And the real de facto way to do it nowadays is with EVPN. So we'll kind of finish off that section with talking about EVPN and the different options for multi-homing there. Okay, so for layer 2 protocol propagation, so we've kind of talked about this with BPDUs already, but protocol propagation is the process of the PE forwarding on the customer's layer 2 protocols that are normally peered. So, under normal circumstances, a device sends some kind of layer 2 protocol, such as CDP, and that's a kind of a link local protocol. The directly connected device will process that and say, okay, I've discovered a CDP neighbor, etc. So there's many different protocols like this that are really meant to be link layer: CDP, LLDP, VTP, LACP, um, and the problem is that the service provider wants to provide a fully transparent service. So most of the time, the service provider is actually going to forward these on, or you could say propagate these frames. You can run into problems where, let's say this is just a EPL, a point-to-point circuit between these two devices here. Maybe the customer calls you up and says, "Hey, you've provided this service to me, and I can put IP addresses on each side, and I can ping, and that works. But LACP isn't coming up. Why isn't LACP coming up?" Well, it's probably because your PE here is not propagating the LACP BPDUs or LACP DUs. Um, so you're gonna have to go into the PE, and there's probably some setting to forward layer 2 protocols. You might want to forward all layer 2 protocols, or you can maybe just select LACP. Um, but there's usually a platform default that you should be aware of. You should be aware of the default with the different platforms you're using in your network because they can vary. So let's talk about from a Cisco perspective. IOXXR will forward all layer 2 protocols by default. And the way I think about this or rationalize this is that with IOXXR, we do a subinterface and we do the keyword L2 transport. This is not just like a normal subinterface, but a layer 2 transport subinterface that's going to be used in a layer 2 service. So I kind of rationalized that, well, with layer 2 transport, we're really forwarding all layer 2. This subinterface here is not used for peering. So that kind of is a way that I remember and kind of rationalize why IOSXR forwards all layer 2 protocols by default. And the kind of difficult thing with IOSXR is that if you want to change this behavior, you actually have to use a layer 2 access list, which is a little bit annoying. That let's say you want to actually drop BPDs. So, if this is an IOSXR router, by default, you don't do any kind of layer 2 protocol propagation config at all. This site sends a BPDU, and it's going to propagate to all remote sites. Let's say you actually want to isolate spanning tree on each site. Well, the only way to do that on IOSXR is that you're going to have to create a layer 2 access list. You're going to have to look up the destination max of the protocol that you're trying to block, So in this case, you'd identify the two spanning tree MAC addresses, most likely the IEEE destination MAC address for spanning tree and the Cisco per VLAN spanning tree MAC address, and create an ACL that denies traffic destined to those two addresses, permits everything else, and then apply it as an ACL to that layer 2 subinterface. So IOSXE has completely opposite behavior. I've got some documentation here for the ASR 900 series. These are kind of small routers that are IOSXE based and used in service provider networks quite often. Kind of small PEs is their role there. And this is the default behavior. So basically the summary is that if it's tagged, if it's a service instance or an EFP, you might call it, the default action is to drop these frames. If it's untagged, the default action is to peer. So actually no default is to actually forward them on. So this is where you can run into an issue with customers, is that if you're not aware of this, you'll just install the router, do the normal config, get the service up, but then, hey, why isn't LACP coming up? Why isn't spanning tree BPDUs propagating? And you'll have to research and figure out, okay, well, on this platform, the default is to drop them. And almost 100% of the time, I would say, you're going to use a tagged service instance on the PE, because you almost are always going to have a NID here, and you're almost always going to want to manage that NID, and you're going to do that with some VLAN. So let's say you've got VLAN 100 is your NID management VLAN. Well, that means you're going to have to use some other VLAN for the layer 2 service. So most of the time, this NID here is going to push the S tag of that VLAN. Let's say your layer 2 service S tag is 50. So this NID pushes VLAN 50 on top of any traffic coming from the CE. So in this PE here, you're going to have a service instance where you're going to have service instance for VLAN 100. That's going to be the management for the NID, and VLAN 50, which is going to be the VPLS service, let's say, for this layer 2 service. So that's why it's almost always going to be a tagged Ethernet flow point service instance on the ASR 900 series, or if you're using some other IOSXE based PE here, and it's going to drop the traffic. Okay, so how do you forward it? Well, there's actually a nice command here on IOSXE, which is this L2 protocol forward command. So you just go under the service instance and you do L2 protocol forward CDP or LDP or LACP, probably for this case where the customer can't peer with LACP between their sites. And there's also a kind of a macro where you just do L2 protocol forward, hit enter, and then you'll see in the config that it actually will automatically denotate every single layer 2 protocol that's possible. So that's something that I see quite often, which is just create a fully transparent LAN service and just forward all layer 2 protocols. And you'll also need to keep in mind that on IOSXE, you might need to go into the VFI and specify layer 2 protocol forward there as well for this to, I guess, for it to also propagate on the pseudo wires. So with so now we kind of understand how layer 2 protocol propagation works. I guess I should also just quickly touch on the different actions that you can do with layer 2 protocol propagation. So you can either peer, forward, tunnel, or drop. Of course, drop is quite obvious. Just you receive it, you drop it. Peer means you want this device here to run that protocol. So if you want to peer LACP, then that means that you want to run LACP between this CE and this PE right here. Forward is the same thing as propagating. It means that you're going to propagate it onto the other sites. And tunnel means that you're going to encapsulate that frame with another destination MAC address. This is kind of most likely going to be a proprietary thing. You're going to want the same equivalent device on the other end, on the egress end, to pop off that tunneled layer 2 header, and this is to bypass devices in the middle of the path that might process that This is very useful when you have, you might not realize that you have this problem because maybe you have some kind of layer 2 access, layer 2 aggregation switch in the path. And that aggregation switch could try to, is going to absorb um, the spanning tree BPDUs, let's say, or LLDP. So you might actually go into that aggregation switch and you actually see all the LLDP neighbors. Nobody really knows that this is an issue, and nobody really cares. Maybe it's just the default behavior. The customer has LLDP enabled, and the aggregation switch has LLDP enabled, and you can see all these neighbors from other customers on their layer 2 services. So it's kind of a tricky thing sometimes, and that's something that layer 2 protocol tunneling helps solve. Is that you just kind of tunnel past that aggregation switch to bypass its processing of those frames. So then the only question is, should you do layer 2 protocol propagation or you shouldn't? Maybe you've got a mixed devices in your network. You've got iOS XR and iOS XE or some other vendor, and they all have different defaults. So what should you do? Well, most of the time you would want to propagate layer 2 protocols. You want to create a transparent LAN service. Of course, there's the other side of the fence, the argument that you want to contain spanning tree instances. You want to isolate sites so that instability of spanning tree on one site is not propagated onto another site. There's that argument too. So there's really no 100% right or wrong thing, but in general, the more transparent of a service you provide, the less issues you cause for the customer. We've kind of talked about this in the previous part, that generally the philosophy is usually that you don't want to block any of the customer's traffic. You want to forward everything, and the customer should have the power to decide whether they want to isolate spanning tree at their sites and things like that. Okay, so now let's talk about storm control. So storm control is a very useful feature. It's basically just a policer for ingress bum traffic. So you just set some police rate for broadcast, unicast, and multicast traffic, and you apply it to the same surface instance or sub interface for the customer's layer 2 service. You might set some kind of rate like 500 packets per second, 5 megabits per second, 2,000 packets per second. Something that is, of course, going to allow necessary traffic to flood. But if there's some kind of an actual storm, some kind of temporary loop, it's not going to allow this loop to continue to grow and grow and grow and reach some high forwarding rate. You might wonder, well, is this kind of a useful thing to handle loops? Like, let's say the customer, forget about this redundancy here. Each site just has one access circuit. When the customer goes, okay, I'm going to order this backdoor circuit between the two sites for some redundancy. And yeah, let's just do nothing. Spanning tree BPDUs are not propagated for some reason. But yeah, we'll just have storm control here on these two interfaces, and that'll handle it. Well, it's the same kind of argument that we talked about way back in an old video about Ethernet TTL. Ethernet TTL is a very good thing, would be a good thing to have. But is that a replacement for spanning tree? No, we wouldn't just form loops and allow the frame to loop and loop 32 hops or whatever the TTL value is, and to say, okay, well, the TTL will break it. We won't just let everything loop and MAC addresses flip-flop, etc. So same thing here. You still have the problem of MAC addresses flip-flopping, and and you're going to reach some level. Let's say you set bum policer to 2,000 packets per second, where you're going to hit that 2,000 packets per second. It's just going to stay there endlessly. So it's just a protection that if a loop does happen to occur, you're not going to impact the resources on your PE. And so I would say that this feature should be added the same way that service providers generally add protections such as maximum MAC addresses that are going to be allowed on the layer 2 service, or maximum routes like BGP routes for layer 3 VPN. You might set a maximum number of routes to 200 routes. You might set a maximum number of MAC addresses to 200 MAC addresses. These are all things that the service provider does to protect the resources of their PE router, because the service provider needs to ensure that one customer cannot exhaust resources on the PE that then affects other customers that are connected to the same PE. Well, I would say that storm control is another one of these features that we need to consider in the same manner, because forget about any kind of backdoor link between these two sites and forget about this multi-homing. The customer can loop their network at any time, and the service provider has no control over this. When a loop happens, it could be that this access circuit is just a branch off of this layer 2 network, and this branch is going to be susceptible to receiving this flooded traffic. So you could flood up to the line rate or the service rate of this access circuit. Let's say this is a 1 gig circuit. Well, it's possible that the bum traffic could then be forwarded out this access circuit and received at this PE at 1 gigabit per second. What's the problem with that? Well, now all that traffic needs to be inspected. The destination MAC address is inspected and saying, okay, this is multicast traffic. Well, this is for layer 2 service, for like a VPLS service. So now the PE has to look up the flood list and flood it to all of the PEs, all the pseudo wires to all those PEs in this domain. And it's going to have to do ingress replication. So this 1 gigabits per second becomes now 3 gigabits per second of replicated traffic. CPU spikes, it impacts other customers connected to this PE. This is a very bad situation, and the service provider cannot control this customer sending that traffic. Well, actually, they do have the control. The control is storm control. The control is just a policer for bum traffic. So I would say that you should always configure some kind of level of storm cran traffic. You can configure it somewhat high. You can also configure these in percentages usually. So you can configure it to 20% of the link bandwidth or something. On a 1 gig service, you'd be allowing 200 megabits per second. Anything is better than allowing it to be forwarded at line rate. So generally, you want this to be something pretty low, because it's quite unlikely the customer is wanting to forward multicast traffic at such a high level. So you can set it to 5% of the bandwidth, 2%, something like that. Now, if the customer does legitimately have multicast traffic that they're forwarding over the service, yeah, that is going to need to be taken into consideration. This will drop that traffic. But I would argue that you're going to have that conversation with the customer, just like you would have the conversation with if they need 5,000 MAC addresses to be learned at this site. Well, the service provider standard is to set 200 MAC addresses as the limit. So there's going to have to be some agreement that, okay, yeah, we will set it to 5,000, but maybe because you're using more resources on our router, there's some kind of upcharge, etc. And then we should also mention that this storm control doesn't apply to EPLs, to point-to-point services, to virtual private wire services, also called. So let's say there's a VPWS between these two sites, these two devices. This PE here is not doing a destination MAC address lookup. It's not doing any MAC learning. It's not doing any ingress replication or flooding. It's just frame comes in, frame goes out the pseudo wire. So in this case, it's fine if the customer wants to send line rate of bum traffic. Doesn't matter, because it's no different than them sending line rate of unicast traffic, because this PE is not doing any sort of MAC address lookup. So there's no reason to worry about storm control on a VPWS service, although you can configure it because the storm control is on a per port basis. So you can configure it there, and it would impact the customer if they had a high rate of multicast traffic on this point-to-point service. So I would say if it's a point-to-point service, don't worry about storm control. So now let's talk about site redundancy and loop prevention. So the first thing that we can mention here is about some built-in mechanisms for detecting loops that many vendors already implement. So again, let's remove some of these redundant circuits, so we just have one access circuit to each site. The customer plugs in a backdoor link at any time. Service provider has no control over this. One mechanism that service providers or vendors do implement is just to detect the movement of the MAC address, detect the MAC flopping. So if now there's a loop here, and a frame could be learned at this PE, but then again learned at this PE. So you have some threshold usually. So here's like a document from Juniper about detecting MAC moves in a VPLS network. So it's somewhat like BGP dampening, where you have some number of times you're going to allow the MAC address to move over some kind of period of time. You'll allow it to move 5 times within 2 minutes. But more than that, then you're going to black hole the MAC address. So you have like these kind of things like cooling time, interface recovery time, wait time, kind of like the dampening, if you're familiar with BGP dampening. And this is also a thing for EVPN. So with EVPN, there's a little bit different of a consideration that with EVPN, we do allow MAC addresses to move as a feature of EVPN, that there's the MAC mobility attribute in the type 2 route, so that each PE, as it learns a MAC that it knows via another PE, it says, oh, okay, I've learned this MAC. This MAC has just moved to me. I'm going to increment the MAC mobility flag and advertise this out so that all the other PEs know this MAC address has just moved over to me. This is a normal behavior when the customer, moves a VM from one site to another site. You do want to, of course, allow the MAC address to move. But again, just like with VPLS, there should be some kind of maximum number of times you're going to allow this to move. Are you going to allow this to move 20 times in 1 minute? No, that is more likely to be a looping condition more than a legitimate movement of the host from one site to another. So the same thing here, where you just allow it to black hole the MAC address. And then Nokia has a similar feature here, black hole MAC address for EVPN loop prevention. These are all just the same thing. So I just want to mention that is a mechanism that does help handle that situation without us adding any kind of loop prevention or any feature to the routers. Okay, but now let's talk about what things we can do to permanently, to allow the multi-hoping to happen. So the first way is to just run spanning tree with the customer. And I mean this in a little bit of a different way from the last video, where I was saying, with a layer 2 access network, this service provider might have to run spanning tree with the switches in the access network with the customer. This is actually a little bit different, because the PEs could theoretically run spanning tree with the customer in that customer's instance. So like this PE here and this PE here could both run spanning tree, but just for this customer's instance. But this is typically not done. Typically, the platform you're using will not support this, because this requires a lot of it's quite CPU intensive, because if you have a lot of customers, usually the vendors are saying, oh, we support this many thousands of customers for layer 2 services and things like that. Well, they can't say that they support that many thousands of customers if they're going to have to run a spanning tree instance and support that. A spanning tree instance for every single customer, that's too much overhead. Well, you might say, well, what about just propagating the BPDUs then? The PEs don't run spanning tree, but they just allow the BPDUs to propagate from one circuit to another, and then the CEs will naturally consider that as a link between themselves and run spanning tree accordingly. Well, you can do that, and that is a solution, but it's not the best solution. This documentation on Cisco has some good points about this. So it's saying what we just said here. It's possible for the gateway devices, and the gateway devices, it means the PEs, to participate in spanning tree, but it's undesirable due to memory and CPU resource that would be required to do that for every single customer. And then it's possible for the PE devices to tunnel the BPDUs between the legs of each of the access circuit. But there's 2 problems with that. One is that there's no direct connection between the 2 switches. There's no direct connection here, although the BPDU is forwarded from here and received here. But if this link goes down, if this link goes down, this switch here doesn't detect that directly as a link going down. So it's going to require the hellos to time out. So if this is rapid spanning tree with default timers, it's going to be a 2-second hello, 3 have to be missed. So it's going to be a 6 seconds to detect that. So that might be too long. That's not very fast conversions. Um, the other problem is that the PEs don't participate in the protocol, so they're not processing the topology change notifications as they are sent from the access network. So it can lead to you relying on the MAC address timeout, which is 5 minutes by default. So this is just saying that if there's some host here, and this host over here is known via this PE. Well, let's say this switch here gets somehow disconnected and it no longer has reachability to this host. It's going to send a topology change notification via spanning tree if it's running spanning tree. This PE is not going to process it, though. It's not processing spanning tree topology notifications by default. So it's just going to keep thinking, oh, if I receive a frame destined to that host, I'm going to send it out that port. It would require this host to send some kind of bum traffic so that this PE processes it, or send some kind of unicast traffic. Let's say this PE has another site for this customer layer 2 service over here. It would require this host to send some kind of unicast frame to this other host for this PE to update that this host is now known via this PE and not itself. So in the worst case, it's going to require the MAC address to time out. So this is also not a very good solution either. Although it is a solution, it's just that handling failover conditions takes a very long time. So there's some better methods. One better method is to run the access gateway protocol. So MST access gateway, AG, or prevalence spanning tree access gateway. So this is a solution where the PEs just run a very lightweight version of spanning tree, meaning that they just statically send BPDUs into the access network to force the access network to block redundant links and for spanning tree to do its job and create a loop-free topology. And they also do the one processing job of receiving topology change notifications and processing and doing a MAC flush. So with the access gateway feature, each of these PEs reports some kind of connectivity to like this fake route. Like you just say this fake route that has, the spanning tree bridge ID of all zeros and priority 0 or something. So nothing's better than it. And each PE just reports connectivity to these routes. And you might configure one PE to have a worse bridge ID or worst cost of the route, something like that, if you want to control which link is used and which link is standby. Because remember, with spanning tree, it's inherently an active standby technology. So one of these links is going to be active and one of these links is going to be standby. Or, I mean, it's possible that that's more the case if you're connecting to like one CE. But, in this case, it could be that maybe this link is blocked, so and possibly they're using both of these circuits. So that is possible. But anyways, they just send these static BPDUs, and these switches converge on the spanning tree topology, and block redundant links to create a loop-free path. So the catch is that with MSTAG, you might have to configure a VPWS like X-Connect between these two PEs. This is needed when you've got a dual home network. So sometimes we call these two CEs a dual home network. We call this setup where there's just one CE a dual homed device, because it's just one device, one CE, versus the network is dual homed, the site is dual homed, so that's more than one CE. So in this case, with a dual homed network, it's possible that the access network gets, partitioned like we were talking about before. So let's say this switch gets isolated. It's disconnected from the access network, but yet it still has an access circuit up. And maybe there could even be hosts connected to this switch these hosts are now disconnected from the rest of the site. It's going to send a topology change notification. This PE should forward that topology notification to this PE as well, so that this PE can receive the topology change notification and also propagate it to the rest of the site. To do that, we need some mechanism to propagate the TCNs. And Cisco and iOS XR, you just put the untagged interface into a pseudowire and X connect with the other PE. And so this is because with MST, the BPDUs are sent on the untagged interface. They're not tagged with a VLAN. Remember that with MST, you configure mapping of VLAN ranges or a list of VLANs to instances. And this BPDU contains the digest of those mappings to ensure that all devices have the same mappings. And there's just one BPDU sent on the untagged interface. So this is why it works with MSTAG to have a dual homed network. But you can't use this trick with per VLAN spanning tree access gateway. So if you're doing per VLAN, the BPDUs are sent on a per VLAN basis. So you cannot put the tagged subinterfaces into a X connect with the other PE because that actually is receiving the customer traffic. So that's the difference here, that with per VLAN spanning tree, the BPDUs are sent on the same VLAN as actual traffic. With MSTAG, they can be sent on a completely untagged interface that doesn't have the customer traffic. So per VLAN spanning tree does not support a dual home network where there's multiple CEs. Per VLAN spanning tree access gateway only supports this situation where there's just one CE, because you cannot propagate the TCNs between the PEs. So I think that covers the spanning tree access gateway solution. It's quite an interesting approach. It requires quite a lot of background knowledge. You have to do some research into how this works. You have to really think about how am I going to configure all the different parameters of spanning tree, because on each of these PEs you have to configure, here's what the root is, here's what the port cost is, here's what the bridge ID is, here's what the port priority is, and things like that. And you just have to statically configure all these values so that the PEs can send these stacked BPDUs. So it's quite a lot of it can be a lot of work to get it up and to understand how it works and how it's going to handle failure conditions and stuff. But it's a much better approach than just allowing the BPDUs to propagate between the CEs and the site. Okay, so let's go over another solution, which is multi-chassis lag. So multi-chassis lag is a very proprietary thing, very platform dependent. It requires some kind of a control channel between the two devices, because they usually have to do tasks such as electing, synchronizing the LACP system ID, synchronizing MAC address tables. If a MAC address is learned on one device, the other device should learn that MAC as well. These two devices have to act as if they're one chassis, one device, as if these are two separate line cards kind of on the same system. So as one system learns a MAC address, it should immediately tell the other system via the control channel, hey, I've learned this MAC address. You should need to configure that this MAC address is known via this port channel. They might have things such as config consistency checks, things like that. So these are all proprietary things that are not open standards. So multi-chassis lag is always going to require LACP. And on iOS XR, it only supports active backup. I haven't come across explanations as to why this is. I believe it's because iOS XR, they probably just lack the all of the implementation to handle, synchronizing MAC addresses between the devices. I guess it's more simple just to say one's active, one's standby. If it needs to fail over, we're just going to do MAC flushes, and then relearn MAC addresses again, versus doing this MAC synchronization and allowing all active forwarding. Okay, so let's say we're doing multi-chassis lag between this PE and this PE. So these each statically configure the same LACP system ID. This CE here puts these two links into the bundle, and they both come up. Well, actually not quite, because this is iOS XR. One is going to come into active, and one's going to come into out of service. So the standby PE sends like a LACP out of service status, so that only one leg of the bundle is active at a given time. On OSXR, this requires an LDP, like a target LDP session between the two PEs, and it uses ICCP interchassis control protocol to handle electing the PE that's going to be active and standby and things like that. There's quite a lot of things that can kind of go wrong with this that you need to be aware of. Things like what happens in a split brain scenario. Also, you have to handle things like if, let's say, this PE right here is active. Well, what if it loses all of its uplinks to the service provider network? We don't want that to still be the link that's receiving traffic because this PE has lost reachability to other PEs. So you can do things like uplink tracking, or might be called like backbone interface tracking or something, so that if these interfaces go down, it actually signals this down, and then this PE, upon losing connectivity to the active PE, will go active. You need to know how the vendor has handled split brain scenarios and things like that. I think on iOS XR, there's also considerations like if this one is active and this one is standby, but then this one goes down, this one will continue being active. But then if you reboot this one, it's going to come back up and say, I can't find any multi-chassis lag partners, so I can't go active. And then you get a situation where both of these links are not being used. So there's just a lot of ways that this can go wrong, and that you have to be, you might just need to do some research into how it works to really feel like you understand it before you implement it. So now let's go into like standards-based methods to do multi-homing. So the first is VPLS multi-homing, and I don't have much experience with this because actually Cisco does not support this, but other vendors do support this. So like Juniper support this. It has a page on VPLS multi-homing. And as far as I understand, VPLS multi-homing is just a single active solution. So basically, there's some kind of extra attributes that are added to the BGP routes, and the all routers elect one PE as a designated forwarder. And actually, the RFC for this actually uses this term DF election on the PEs. So I believe this was kind of a precursor to multi-homing with EVPN. So it's just single active. In this case, maybe this PE is selected as active. This one is going to go to standby. And I believe the PEs just set up a pseudowire with the active one. So they only have a pseudowire to the active one, maybe. And then if they see this PE goes down, then they set up a pseudowire to the other one. Or, there's just some kind of mechanism to handle the failover. But the important point is that it's only a single active. So as you can see, almost all of these solutions so far are single active. We've got MST Access Gateway, which is probably going to be single active. Maybe it's not, but you're not using all links, of course. Multi-chassis lag, where Cisco iOS solution is just limited to it's to single active. EPLS multi-homing is single active. So now we get to EVPN, and EVPN is the only one that's like really supporting all active. Of course, multi-chassis lag generally on other vendors can be all active too. But EVPN is a standards-based alternative to multi-chassis lag. You can even use PEs from different vendors. If you want like the ultimate kind of redundancy, sometimes people will say, okay, I want a Cisco PE and a Juniper PE or a Nokia PE or something like that. Well, they will interoperate with, and because they both support EVPN in its standard space, so you can do all active with PEs from different vendors. So EVPN multi-homing can kind of take a while to explain, but just to go over the brief concepts, let's talk about all active here, and we'll talk about this site here with one CE. So one PE will be elected as DF, designated forwarder, and that's going to be the only PE that sends bump traffic onto the site. And the non-DF is going to block bump traffic from being forwarded onto the site. But then there's some more complexity that needs to be added because situations like, let's say this PE is the DF, this one is not right here. Well, let's say the CE decides to send bump from this way. Remember, this is a bundle and it's all active, so both members of bundle are up. C just sees a bundle as being up, and the PEs have to statically set the same LACP system ID. So this non-DF receives the bump frame. The thing is, it has to flood it to this PE because this PE has another site in this layer 2 service. So that site needs to receive the bump frame. But also, we don't want that bump frame to go back to the customer site. So there's like a split horizon label that the non-DF puts on the frame. So the DF doesn't send that back to the same site, but it does send it to another site. And I haven't mentioned the term yet, ESI, the Ethernet Segment ID. So the two PEs know that they connect to the same site via the same Ethernet segment value that they configure. So that's what sparks the DF election. There's also a thing called EVPN multi-homing alias label. So let's say this PE here, via the type 1 routes, it's going to see, oh, okay, these two PEs are connected to the same site. And I've learned a MAC address maybe from the DF here, a unicast MAC address is reachable, but I see that this other PE is connected to that site. It hasn't advertised the type 2 MAC address yet, but I do have the alias label that it advertised in the type 1 route, so I know that I can actually load share traffic to both of these PEs. That's another kind of complexity that this added to EVPN to handle all active multi-homing. So that's most of what there is to all active multi-homing. There's two other modes with EVPN. So EVPN at first only supported all active and single active multi-homing. So with single active, it means that one link is active, one link is standby on a per VLAN or per EVI basis. And this is not like multi-chassis lag where one link is LACP out of service. It actually just means that the non-designated forwarder is just not allowing traffic in and out. So the customer, typically this might actually just be two completely separate links, no bundles. You might also see this in documentation as two separate bundles. I suppose they're using a single link bundle just to as a way to use LACP to handle link failure. I'm not too sure. But let's just say these are single links. Well, the CE is going to have both of these links in the same bridge domain. So when it has a bump frame, it's just going to flood bump traffic out both of these links. But this is the DF here. It's been elected for the DF for that VLAN or that EVI. This is the non-DF, so it's just going to drop the traffic. It's not going to forward it on. If there's any traffic destined to this CE for some reason, it's not going to forward it out that link. So you just created a true just active standby situation. But it's on a per VLAN or per EVI basis. So you can kind of load share. You can have VLAN 10 active on this link, VLAN 20 active on this link. There's an algorithm, some kind of formula that the PEs use to elect DFs on a per VLAN basis. And you can actually control this. You can kind of set priorities to control which PE is active or standby on a given VLAN or EVI. This is sometimes called service carving. And the reason you might choose for single active instead of all active is that you have to enforce a CIR. Maybe these are 1 gig links, but the CIR is only 500 megabits for the total for both links combined. So you can't really do that with all active. You can maybe set this link to 250 and this link to 250, but then a single flow is going to be limited to 250 because they can't use both links at the same time with LACP. So that's why you might use single active, that you want the redundancy. You don't really care about, since the connection is metered to 500 megabits anyways, you don't really care about using both links. You want the redundancy, but you want to be able to meter this one link to 500 megabits per second on a per VLAN or EVI basis. Now, the next step is port active. Port active was an addition that came after the original spec allowed for all active and single active. And port active, it's now per physical port. And I think this is actually more intuitive. That with port active, you just have this port is active and this one is LACP out of service. So it's more clear to me. So all VLANs are using this one link. I think this is probably the more likely option to be used if you need to enforce a particular bandwidth rate, do QoS and that sort of thing. So all of these EVPN methods we've been talking about are just for a single home device, one CE. But let's talk about what happens when you have two CEs. Well, one option is, of course, for the two CEs themselves to do some kind of multi-chassis lag. But let's pretend these are just very basic layer 2 switches and the customer isn't doing that with them. So how do we support two CEs with EVPN? Well, you might think maybe one of these methods, like maybe we can do all active because each PE only has one link up in the bundle. So you can get both of these links up with all active. Each CE uses a different system ID, but that doesn't matter. These PEs aren't, remember, there's no control channel between them. These PEs aren't advertising what the CE's LACP system ID is. It doesn't matter to them. So maybe that would work, but the problem with all of these methods, if you start to think it through, is that if you have to handle link failure within the customer site, if you have to handle a case where one of these switches becomes isolated, this becomes a problem because the DF is the only one that forwards bum traffic. So you can't get the non-DF to forward bum traffic. So, let's say there's a host here and a host over here, and this is the DF. Well, this site has become isolated. So bum frames are sent by the DF. They're not sent by the non-DF, and none of these hosts over here can receive bum frames. If the access network gets partitioned, there's no way to handle this. Theoretically, you could have some situation where the CE is doing some kind of tracking of the link. So if it gets isolated, it actually brings down LACP or something. So LACP goes down here. This link goes down. This PE withdraws this type 1 EVPN route, and then this PE now goes to DF. But you've still caused the problem of isolating this one host here. Maybe there's no hosts. Maybe this is just some kind of aggregation switch that doesn't have any hosts connected to it. So that could be a solution, but that's quite a big ask for the CE devices to support. So really, in my opinion, the only proper method for dual homing with EVPN with two CEs is to use single flow active. This is yet a fourth multi-homing mode that EVPN supports. So there's an RFC for this. So I've got it here. So this document defines a new single flow active redundancy mode. So that essentially the DF election becomes based on a per flow, not a per VLAN. And this sounds kind of confusing at first, but I'll explain it right now. So Cisco actually has a pretty good case study kind of for why you would use this. So here, the two PEs are connected to this ring. Okay, and so the key for single flow active is that the PEs have to participate in the redundancy mechanism. So just like we were talking about before, well, what if the PEs participate in spanning tree? That would solve it. Well, here, the PEs are essentially doing that. They're participating in the link protection protocol. So this is G8032 here, that's handling the redundancy. So this is configured as a half ring. So right now, this link here is blocked, but there's redundancy here. If any other link goes down, this link can go up and restore redundancy. But the site is always going to be partitioned. So hosts off of this CE are going to be reachable only via PE1, and this host here is reachable only via PE2. PE1 doesn't have reachability as it is right now because this link is blocked. So essentially, it's per flow that you decide which PE is active. And you have to actually disable some things like the full-on DF election and the alias behavior where you don't want PE3 to think, oh, host 1 is reachable via both PE1 and PE2 because I see they're attached to the same Ethernet segment. You don't want that behavior. You want it to think, oh only at PE2, not PE1, because PE1 doesn't have reachability. So let's just go over failure. So like this link might go down. Now this link goes up. So now this PE is going to start receiving the flow of traffic, and this PE advertises the type 2 route with a higher local preference. So I believe it says it here that one one PE advertises with a default local preference of 100. The other PE sees that advertisement and realizes, oh, okay, that host is reachable via the Ethernet segment, even though I don't have connectivity to that host. But I'm going to re-originate that and set local preference to 80, so that this is the backup path. This is to allow faster reconvergence upon some link failure in the access topology. So this is quite a complicated mode, but this is really, from what I can see, the only way to handle a multi-CE situation is to have the PEs participate in the link redundancy mechanism and do single flow active. So now, let's say that you really do have this situation, and you have to support two separate CEs for the customer at one site. You're doing EVPN. What should you do? Well, I would look at single flow active, see if the equipment you're using supports it. Cisco does support it on iOS XR. If not, you can consider using the other multi-homing methods, but you might have to have a conversation with the customer that this is going to depend on you not having any link failure within your access network. Now, if this is a very simple case where it's just kind of these two CEs connected and that's kind of it, and they're just like in the same rack in a data center or something, yeah, you could kind of count on the fact that there's not going to be any um, topology change in the customer's access network, and maybe you could do something like you could even do port active or something, and that might be a little bit more simple. You don't have to worry about the complexities of single flow active. And just say, okay, this port is active, this port is LACP out of service. Um, if this link goes down, this link is going to come up just like it would if in this situation where there's one CE. But the key is that these CEs have to always have reachability. We're assuming that each CE has full reachability into the access network. If that might not be the case, it's going to cause the site to become partitioned and cause reachability issues. And this is it's kind of a worse case than just the case we looked at the very beginning, which is like, what happens if you just propagate spanning tree BPDUs between the site? Well, it works, but there's very slow convergence, right? There's 6 seconds of convergence. Yeah, that's kind of slow. There's 5 minutes, up to 5 minutes of unreachability while the MAC address times out. But with this situation, when the site gets fully partitioned, there's no convergence at all. It's just permanently broken until it gets fixed. So that just might be something that you have to consider if you're doing two CEs. So I think that wraps it up here. This last case was quite a tricky situation, so I hope it didn't get too confusing. I hope this was somewhat useful to kind of do an overview of all the different multi-homing possibilities with layer 2 services, and that this video series in general was useful. If there's some kind of topic about this that I missed, something that you think would be good to cover in terms of, spanning tree and loop prevention and redundancy and stuff in this, and from this point of view, from like a service provider's point of view, let me know if it's something that I feel like I understand enough and think it would be good to add. I could maybe add some more content to this series, but if not, yeah, I hope this has been useful.